All right. Hello, everyone, to the third lecture of online learning, operations, and electronic content. So today we are planning to continue kind of the path that we started. And just to recap, we talked about various notions of correlated equilibrium last time. And then if I have learning agents and they run certain online learning algorithm with a slightly stronger guarantee than the typical external regret, something that was called swap regret or equivalently up to polynomial factors inter-regret, then you should expect that these agents, they are kind of going to converge to a correlated equilibrium. And if they just run no external regret learning algorithm, they're going to converge to a weaker notion called coarse correlated equilibrium. This is great, but I would say back to how I started last lecture, if you remember. So there was this story about the traffic lights that you're listening to as decision-making agents and try to follow what it is guiding us, and eventually you want to have some sort of meaningful behavior as a group. That doesn't completely fit into the story because somehow the traffic light needs to suggest a correlated distribution to all of these agents, and then they need to do some calculation to make sure it's at equilibrium and convince themselves that this is the right strategy to play. So what I'm going to talk about today is a little bit of a difference of the abstraction in the sense that now I'm imagining that, have you guys been to Bobby's talk this week? Raise your hand if you heard it. That was the perfect introduction for this lecture. So I'm really thinking about separating forecasting and decision making, not asking that much from the decision maker and putting all the burden on the shoulder of a learner / a forecaster that is trying to forecast the information that is needed to give to the agent. So I'm going to start by what I call a simple setting for decision making under forecast. That's the first thing we're going to cover today. And I'm going to tell you how this setup, even though this is about kind of a one-on-one interaction between a forecaster and a decision maker, is related to learning in games. So we're going to talk about learning agents in games with forecasts. And you will see soon how we are completely with it. So once I set up the problem, then we are talking about how to design forecasters. So this lecture is mostly about how to design a forecaster. And as a forecaster, someone who is giving some information to your agent or maybe group of agents, you would like to induce certain behaviors when they make decisions. So we're going to talk about how to induce what I call no external regret behavior using forecasting. And I want to actually teach Follow-The-Perturbed-Leader in one of the future lectures on online commercial optimization. So I decided to combine that algorithm with this setup. Now there's a new algorithm. There might be a bug in the proof. Hopefully there is no bug. So it is kind of like a new thing. I decided to teach it in the class. Somehow we will hit two birds with one stone. So in order to design this forecaster, therefore, we are going to learn this forecaster, which I'm going to call it State-Perturbed Follow-The-Perturbed-Leader. Goes by the abbreviation of State-Perturbed-FTPL. For those of you that are familiar with Follow-The-Perturbed-Leader algorithm for full information adversarial online learning, it has a lot of similarities to that, but it's not exactly that. Kind of like my goal is to induce Follow-The-Perturbed-Leader behavior by a certain forecast. And then this is great, but we already know that no external regret is not like the best notion of regret you can expect for, especially in games when you would like to induce a correlated equilibrium as the good behavior on the agent. So we're going to talk about how to induce no internal regret via forecasting. And that brings us to what Bobby was talking about in his talk, a very important concept called calibrated forecasting. So I'm going to call it calibration in forecast. And for reasons that will be clear, we're going to call it also FV calibration. That's how in micro theory people usually refer to this notion of calibration. FV stands for Foster-Vora, goes back to the classic work of Dean Foster and Ricky Vora in 1998, which introduced this notation. So sometimes I will call it FV calibration, or maybe just like calibration. And then in this class, we learned one mathematical tool which turned out to be very powerful, and that's Blackwell approachability. So I'm going to show you how you can basically reduce calibration through Blackwell approachability. Through Blackwell approachability. So this is kind of an ambitious plan. Hopefully I can finish all of the details. I might postpone some of the technical details either for the assignments or for you guys to think about offline. But let's see how far we can get. All right, so here's the simple setup I would like you to think about. And for the purpose of this lecture, just to keep things simple, I'm really thinking about binary states. So imagine there is an environment. On one side, and then there is this guy, an agent sitting on the other side. So the agent is trying to maximize utility and is taking actions. Imagine, just for the simplicity, that as an agent, I have a utility function that depends on not only my action, but also somehow on an unknown state of the world, which I'm gonna call it X. So this is my action, which you should think of as an element in, let's say, set curly A. And then this is a state. And for the purpose of this lecture, I really think about this state X as being binary. So it is either 0 or 1. So imagine you want to decide whether you drive from home to campus or you're going to use a bike. And it depends on whether it's a rainy day or not. If it is a rainy day and you decide to bike, then you're going to get 0 utility. If it's a rainy day and you decide to take your car, then it's going to be 1. If it's not raining and you bike, then this is good for your health. You're doing an exercise, so you get utility of 1. And then the other last case, when it is not raining and you take a car, you're not environment friendly, you get a utility 0. Right? So that's kind of like the setup. But then the catch is, as an agent, you don't know the state exactly. Think of it as an unknown state. And then there is a forecaster, this guy sitting here, that is doing some research on the environment. And the forecaster is providing you with essentially a forecast. I'm going to call it X hat. And in my work, agents are very simple. So they have myopic behavior. So once they receive a forecast, all they do, the myopic agent, they best respond to the forecast. Myopic agent is going to pick an action, A hat, which is a best response to X hat. And just be a little bit more careful. Sometimes most of the times actually, I'm gonna use p hat because this forecast might be probabilistic, and you should really think of p hat as being the probability that x hat is equal to 1. So I might actually suggest the probability that x hat is equal to 1 rather than just a random realization of x hat. And in that case, a hat is going to be kind of the best response to p hat. And what are these best responses? So this is basically nothing but just the argmax of my utility function when I imagine my state is actually x hat. And this is my utility function when I assume my state is drawn probabilistically from distribution. And I've used the notation a little bit just as a convention. So every time I use a 0, 1 as the state, think of it as the realization of the state. Every time I use a probability, think of it as a probability. So in other words, I'm just gonna use this convention that u of a and p is defined to be expectation of u of a and x, when x is drawn from p. These things are binary, so x drawn from p means that x is going to be Bernoulli random variable with probability of 1 equal to p. Okay, that's the setting. And then, so forecasting is not a one-shot game; it's actually a sequential game. There are going to be sequence of sequential forecasting, sequential forecast decision-making game. Basically, the following sequential game for time t from 1 to capital T, think of t as finite horizon. At each time t, the forecaster sends a signal, we'll call it PT hat, to the agent. Then the agent takes the action a T hat, which is one of the actions that maximizes agent utility when the state is drawn from distribution PT. And then unknown state of the world, the real unknown state of the world at that time, unknown state, is revealed to the forecaster. And you should really think of this forecaster as an online algorithm for learning the forecast. So there's a sequence arriving unknown x1, x2, all the way to x capital T. So unknown states, which I'm going to call it xt, now is revealed to the forecaster, and now the game continues to the next round. So forecaster knowing xt is going to update the way it sends the signal to the agent, and the game continues. Yes, Vash?
So here, is there a reason that the agents are myopic?
Yes, I guess the way I think about that is the agent really don't see anything of that environment. So you look at, I don't know, the weather forecast in the morning, whether it's rainy or not, and you have no idea how the day comes. So you have no access to the history in some sense. Otherwise, if I kind of give access to history to the agent, let's say the history of these realized unknown states, and I ask the agent to do something more sophisticated, then the agent can run an online learning algorithm and do what I want the agent to do. The beauty of this setting is kind of like separating the environment from the agent. It is really a meaningful setting when the agent doesn't see the environment. And that's actually the perfect introduction to these bullet points, where I talk about learning agents in games, because somehow we are playing a game Now, what the forecaster does is telling you something about what the others are playing. Like imagine that other players in the game are playing a profile of the strategies. Imagine it is a mixed profile, so there is a distribution over action profiles of other agents. Then the forecaster essentially forecasting what that profile of the strategies are, or is giving a distribution. This entire setting can be generalized to when you have non-binary states. And that's kind of the case that I have more than maybe one opponent, and that opponent has more than 2 strategies. Maybe there are like 5 opponents, each of them has 4 strategies. That gives me 4 to the 5 possibilities for the action profile of others. And then the forecast is a randomized prediction of that profile, somewhat distribution over all possible profiles. And the forecaster tells me, hey, this is what your opponents are doing. Let's respond to that. And we would like to design the forecasting game such that at the end of the day, if I provide that forecast for all agents, then eventually as a whole, they converge to correlative equilibrium. Or converge to coarse correlative equilibrium. You're inducing noise. So this is the kind of setup that you really don't know what others are doing. They're playing a game, maybe you don't even know who are your opponents.
Is there a version of this that the forecaster provides, like, let's say, an estimate of like a horizon? Let's say next 5 periods, there is a, I'm planning for my next week, how to make it. Then it provides me with like a.
Right, so there are extensions of this model where the agent assumes to have a memory. And in that case, the forecaster can provide you with more than one prediction. And then it's gonna stay your memory for some time, and it's gonna be dropped down after. But this is not the one. Any other question? Good. So as you can see, as a forecaster, I'm inducing a behavior. Basically, if you fix a sequence of unknowns x1 to xt and a particular forecaster algorithm, then you will have a sequence of actions a1 to xt. Right? So this should remind you somehow of online learning that this is the unknown part that you're trying to learn about, and then you take actions to maximize reward. So now I can start thinking about, for example, agents regret. Okay, so let me reform all. So my goal is to design online forecasters that induce quote unquote good behavior. So to formally define the good behavior, let me actually define agent external regret as a function of P. So this is defined as the following. So imagine you knew the entire sequence x1 to xt up front. There was one fixed action that you would have benefited from that the most. In particular, I'm looking at max over all actions A in the curly A that maximizes maximum all actions, that maximizes the quantity from 1 to capital T, utility of the agent taking action A in all rounds when the state is xt. And then you can start comparing that with basically the utility that you get when you pick action, which is the best response to PT hat when the state is xt. Okay. So P1 hat to PT hat, this is the sequence of forecasts in that case. And x1 to xt is the sequence of unknown states. And we kind of say this forecaster with respect to this sequence is giving a small agent external regret if this quantity is a small. In particular, we say agent external regret T is at most epsilon if this quantity is at most epsilon. Right? This is the definition. And our first goal is to design an online forecaster that kind of like make this quantity small in the sense that I'm going to induce a behavior as if the agent was running an online learning algorithm. The agent, the pattern was talking about, imagine an agent that has access to history and therefore could run an online learning algorithm to pick the right sequence of actions. Now, I want to design a forecaster that the agent will behave like that, even though my agent is actually very simple and very mild. Is the goal clear? Okay. And now let's see for a second why some very naive ways of forecasting this quantity does not work. And imagine that you're thinking about binary games. Oh, before I can actually give you some examples to just make sure we all understand about this setup. So example number one is the one that I was talking about. My XT unknown state is whether it is rainy or not rainy. So whether it's raining or not. And then my actions are, say, even they are binary, so it's either biking or going by car. And then the utility function is as I described. So utility of rain and bike is going to be equal to 0. Utility of rain and car is going to be equal to 1. Utility of not rain. Okay, so action was the first thing, so bike, rain, E and R, and then utility of biking, not raining is going to be equal to 1 again, and then utility of car, not raining is equal to. That's example number one. And example number two is something that came out of the discussion with Arshan. It is a game. So example number two, and you can generalize this to any normal form game. Imagine I have 2 players. I'm looking at the board from the perspective of agent 1, player 1. So therefore, my XT, there's a 2-player game. Let's say action of the first player can be either 0 or 1. Action of the second player can also be either 0 or 1. So if you want to cast this as kind of like a forecasting with a decision-making agent, you can think of your forecast XT to be equal to the action that, sorry, the unknown state of the action that player 2 is taking every single round. And you can think of your action to be basically the action that player 1 is taking every single round. So there are 2 players playing. So one of them I think of it as an environment, and the other one is taking as actually the agents. So as a forecaster, I see the previous history of plays of player 2, and I will tell something about that player 1 in the form of a sequential forecast. And then once I provide the forecast, player 1, all it does is best response. And imagine we can do the same thing. So now I can sit in the other side, interact with agent 2, look at the history of agent 1, and say something about agent 1 to agent 2. And for example, if I can design a forecaster algorithm that satisfies the small external regret, and I do that for both agents, then they're going to run essentially no external regret learning algorithms. And as a result of that, they're going to convert to course correlated equivalent. This is something that we studied last time. And then you can think of the internal regret version. I'm going to talk about it later in the lecture. And if I manage to have a small internal regret, agent internal regret by a way of forecasting, they can do the same trick, and then my learning agents are converged accordingly. Okay, so that's kind of like a plan. So now let me show you why some naive forecasts are going to fail. and in particular, any deterministic forecasting. So what's the simplest deterministic forecast? You get to see as a forecaster history of these 0 1s, and you want to forecast whether it's raining or not, giving me a number between 0 and 1, what would you do? The most I think.
Majority vote.
Majority vote is 0 or 1, so that's one way of doing that. Imagine you are allowed to give a number between 0 and 1. What's an alternative? Empirical average, right? Just like reporting the empirical average. That's maybe the most naive forecasted. And I'm going to show that this is going to fail badly. Let me explain why such a thing is going to fail badly, and why in general any deterministic forecast is going to fail badly. So this sequence, you should really think of the sequence that is generated by an adversary. So now, if the forecaster is doing something deterministic, then I can do the following as the adversary. I can see, hey, if I forecast this, then the adversary, then the algorithm, the forecaster is going to suggest this to the agent, and the agent is going to pick this action, right? So for example, the agent is going to go with biking, and I can actually simulate that. At time t, before releasing xt, I can decide whether the agent is going to bike or use the car. And if you're this malicious god or adversary that can decide on whether this is going to rain or not today, and you know that you already know the guy has decided, the destiny tells him that he's going to bike or ride, then you're going to just do the opposite. So if he's biking, you're going to rain. If he's driving the car, you're going to make it sunny to screw up the person. So this is kind of like a proof in words that's why no deterministic forecasting can work, because as an adversary, I can always shoot you the worst thing. Formally, for example, think of the empirical mean, which is actually a deterministic forecast. PT hat would be equal to what? So 1 over t minus 1. Note that you only know as a forecaster the sequence 1 to t minus. So 1 over t minus 1, t prime from 1 to t minus 1, xt prime. Okay. Now I should do this sequence. So let's say x1 is equal to 0. I'm looking at kind of this setting, and let's say this is 0, this is 1, and let's go with 0 1 fractions as well. So let's call this 0 and let's call this 1. So x1 is 0, x2 is equal to 1. I'm going to alternate. x3 is equal to 0, x4 is equal to 1. And okay, so you start as a forecaster by sending this signal. So now P1 is going to be, it can be anything arbitrary. So I'm going to go with maybe 1. You're here, now P2 is going to be equal to 0. Is it clear? And then here, P3 is going to be equal to half. Now P4 is going to be something smaller than half, and then the game continues. And then when you think about the decision maker, if I give you a probability for rainy or not rainy, if the probability is greater than half, the best thing you can do is taking the car. Sorry, probability greater than half, that means most likely it's going to not rain. So you're better off bike. Probability is less than half, you're better off take the car. So therefore here I'm going to bike. Here I'm going to use the car. Here I'm going to bike. I'm going to use the car. So on and so forth. But then if it is 0, that means it's rainy, so you are screwed. With 1 that's not raining, you're taking the car, so you're screwed. And basically you get 0 utility. While a more naive agent that was just biking would have received T over 2 over capital P number of times. Therefore, the regret, the agent external regret, in this case would be big omega of capital T. So we linear in T and that's bad. And the same scheme can work to screw up any deterministic forecasting as experiment. So we need randomization. And let's say we want to use randomization. If you just want to fix that scheme, what would you?
Ask it.
Yes.
So I wanted to also ask Bobby, but I didn't get a chance. So here, do you assume that the forecaster knows the utility of the agent? So because
In my design of adversary, I assume that the adversary knows the utility. You can assume that the forecaster knows the utility or not. But I'm going to show you next. I don't need to actually assume that I know the forecaster utility. In many settings, actually, you make that assumption.
So if the deterministic version doesn't work, but we design the forecast in a deterministic way, but we know we use the utility information,
Right.
Can we get rid of this?
Because adversary also knows the utility, and adversary can screw up the forecast. This is actually still a bad example in many settings. Good. Before moving further, I asked a question from the class. Let me actually get the answer first, and then I'm going to show you, kind of like give you a quick remark about this utility function. Any suggestions what to do to fix that scheme? Does anyone know what to do? Yeah, when pre-call mean doesn't work. What would you do? You have to just.
Yeah, we can. I guess I know it.
Okay.
But I think you can. One way is to imagine an additional day and realize that day as a random result.
Okay.
And that will add the randomness to your entire sequence and then take the empirical.
All right. So I guess you're saying add a noise. The suggestion is that this doesn't work. Let's see if I add a noise, little bit of noise with variance that needs to be decided, whether that will work. Before showing you, actually that's going to work. Let me make a remark. So when you think about this utility function, when you have binary actions, and this is actually a specific binary action, u of a and x. So really, this is actually a linear function as a function of x. Why? Because you can always write it down as u of a and 1 times x plus u of a and 0 times 1 minus x. And in fact, if I look at the probabilistic version, so I had u of a and p, which was equal to the expectation of u of a and x. And if you guys ended up teaching this code at some point, if I had to pick a different notation for you, I was just lazy, I picked the same u, this is mathematically wrong. But bear with me. Mostly we're just going to work with the version that the second input argument is the probability. So it's fine to have this conversation. So u of a and p is this, right? And then this is going to be exactly equal to, again, p times u of a and 1 plus 1 minus p times u of a and 0. So this is really like a linear function of a p. And this turns out to be important in most of the arguments I'm going to talk about. So that just as a technical remark. And now let's suggest the algorithm. Our first forecaster. I'm not sure who gets the credit for this. I think the credit should go to Kalai and Vempala, who talked about Follow-The-Perturbed-Leader. I don't think it was really like a new algorithm. We start using that idea in these guys.
course.
I'm not gonna get this one. Oh no. Okay. No idea what. But so, state-perturbed follow-the-perturbed-leader, SP-FTPL. This is how the forecaster works. For t from 1 to capital T, I'm going to set pt hat to be equal to 1 over t minus 1 summation t prime from 1 to t minus 1. And as Mohammed just mentioned, what I'm going to do is I assume that somehow one of these states was a little bit perturbed. Maybe the time 1 is perturbed a little bit now, rather than being xt prime, is xt prime plus some noise. Let's call that nt. It's not a function of t prime, it's just like one noise. Basically, this quantity, but nt. And let's say nt is going to be drawn from uniform distribution from 0 to 1 over epsilon. This is a very high variance distribution. So if you think about the PDF, it's literally from 0 to this point 1 over epsilon, and epsilon is the small to 1 over epsilon can be large and has this kind of distribution. So this is like epsilon. I'm happy that no one raised his hand or her hand and said, Rod, what are you talking about? This is not the probability anymore. How you can add a noise and still claim this is between 0 and 1. And this is indeed true. You cannot add a noise and assume this is between 0 and 1. However, I'm going to make that assumption. Somehow I never said when I'm making a forecast, I have to actually give you a number between 0 and 1. Let's say I can give you any number, like I can give you 1.1, and then you plug that into your linear utility function, and then you pick the optimal action. That's one way of saying this is still a okay scheme. Then the second way, you will see that in your assignment, once you add the noise, project it into the interval 0, 1, and go with that prediction, with that forecast. But it's just going to make the math messy, so I'm going to stick to this version. I tried to find a very clean way of doing the projection version last night. I ended up only finding a clean version of doing this, so let's actually do this one. And then plain with state-perturbed FTPL. If epsilon is said to be something like order 1 over a square root of t, we have the following. The agent external regret would be, as a function of t, would be at most order of a square root of t. And this is great news. The proof of this claim has a bunch of steps, and if you're familiar with the analysis of Follow-The-Perturbed-Leader, is actually following kind of like the same line of argument. And who has seen Follow-The-Perturbed-Leader? Raise your hand if this is okay, good. So for the rest of the class, you are going to enjoy the next 45 minutes because this is one of the cleanest, nicest proofs that we can think of. And there are many ways of doing that. I think this version is a little bit cleaner than the version that probably rather you guys have seen. So let's actually do it. So the analysis is coming from looking at a sequence of what I call hypothetical forecasters. So consider a hypothetical forecaster. Hypothetical forecaster, which I'm going to call it state be the leader. So let me write it down. State be the leader. And what does this do? So it basically suggests a PT bar, which is equal to 1 over t summation t prime from 1 to t of xt prime. Why this is a hypothetical forecaster? Because when you're making this forecast, you don't know xt. I just included xt's, taking an average over everything, including the forecast that you just released, xt. And I make that, and imagine that hypothetically I could make that forecast. So now I can send this to the agent is going to best respond to this forecast. The level. Essentially, I want to say that the agent best responds to the forecast. The agent is going to incur no regret, not vanishing regret, zero regret. Let me write it mathematically. I want to say that summation t from 1 to capital T, utility of the agent, if goes with the best response to PT bar, when the state is actually XB, is in fact greater or equal than any fixed action. T from 1 to capital T, and this is the statement is actually true for any time. So T prime from 1 to T. Utility of action A with state xt prime for every single action. That's the first statement. Is it clear? What does it say? So it says if there was this hypothetical forecaster that is recommending this quantity as the property of unknown, let's say being 1, if I follow this, I'm not going to incur any regret. But then if you could use this forecaster, that would have been great, because then your regret is not even the square root is going to 0. But then the catch is you don't have access to t, xt, so therefore this is just a hypothetical. But it turns out that you can massage this hypothetical forecast and make it a real forecast, and this is indeed a SP-FTPL. So proof of the lemma. And the proof is based on induction. So first of all, t equal to 1 is trivial. Why? Because I know x1 and I best respond to that. It is better than any other action. So utility of best response to basically p1 bar, which is equal to x1 itself. And x1 is going to be greater or equal than the utility of action A. That's the base of the induction. Now, suppose we have the following inductive hypothesis that for every action A, summation t prime from 1 to, let's say, t minus 1, or any really like upper bound that is strictly smaller than t. Let's go with t minus 1. U of best response to pt prime bar and xt prime is greater or equal than summation t prime from 1 to t minus 1, u of a and xt prime. Now I want to show that we can basically have the same inequality when you have t. rather than T minus. Let's see why this is true. So if I look at summation T prime from 1 to T, U of best response T prime bar and xt prime, then you can write this summation as the summation of the first T minus 1 terms together with the last, which is the T that you get by best responding to PT bar, the unrealistic one, right? The one that comes at the end, and this. Now, I think this quantity is basically equal to the following. So it is equal to T times fix that action. Let me call this guy A hat. Just some action A hat with T times U of A hat and PT bar minus summation T prime from 1 to T minus 1 U of A hat and xt prime. Let's see if you guys agree with that. And here I have used the fact that my utility function, the function of second input argument, is actually linear. Why? Because if you look at T times this guy, so this is what? Because it is linear, so it's going to be summation. So it's going to be 1 over T. This is equal to 1 over T, summation T prime from 1 to T, U of A hat, and PT prime. Sorry, xt prime. So T times that would be just be this summation. So the first term is this guy, and then you have to subtract the remainder. Is this clear? So again, so T times this quantity is nothing but just T times 1 over T times the summation. The T cancels, and then this is the first term plus the remaining, so I have to subtract the remaining. All right, and now you can say right, so response
Since some is positive.
that's what I thought as well. Right, so A had the best response to PT bar. I think good. So now I can write it down as being greater or equal than, let's write down everything. So this is greater or equal than T times U of any action A PT bar, because A hat is just the best response to PT bar. So this is going to be greater or equal than T times U of A and PT bar. My notes. Yeah, my notes, I also said this is greater or equal than zero. I don't see it now because it's the best response to PT prime bar. And so this quantity is kind of like what we want to show. So it is going to be right, the summation of t prime from 1 to t, u of a and xt prime. The exactly low round you want to prove. And then you have this summation t prime from 1 to t minus 1, u of best response with respect to pt prime. Oh, that's the induction hypothesis.
Yeah.
Oh,
Yeah.
sorry. You're absolutely right. I am sorry. You are right. So that's the inductive hypothesis. So this quantity, because of the inductive hypothesis, right? So this is t minus 1. I'm comparing the best response with some other action, whatever it is. Best response in that round. So this is going to be definitely greater or equal than 0. And therefore, the whole thing is going to be greater or equal than the summation t prime from 1 to t minus 1, u of a and xt prime. So this is because of the inductive hypothesis. When you compare yourself with the action A hat, which was the best response against PT1. So this is always correct. Now, the next step, let me say it in words because I just don't want to make sure you algebra. I want you to understand what's going on here. So now we know that if I give you this extra information at time t and you do the empirical mean, knowing that this is actually good, you get 0 recurrence. Now, suppose I give you that extra information, and I also perturb your first state. I add the noise now. So you're still be the leader, but I'm going to actually perturb your state a little. And for a second, it's going to be clear why I'm doing that. So then the point is that if I just perturb the state a little bit, this is not going to change the 0 regress of this be the perturbed leader, be the leader. Why? Because somehow we can imagine that kind of similar to what Mohammad Reza mentioned. So rather than starting the game at time 1, imagine the game was at time 0, the game started at, sorry, starting the game at time 1, imagine the game was starting at time 0. And at time 0, your state was perturbed a little bit. Or you can imagine that still the game is capital T number of rounds, but your first state is a little bit perturbed. Now, these functions are Lipschitz. If you perturb that state a little bit, you should not expect a huge difference comes up. And this is indeed the case. So let me formalize that. I guess my point is that when you perturb a solution, this is pretty much like running the be the leader when you have one extra round. One extra round doesn't change the regret that much. Therefore, you should expect that be the leader and a state perturbed be the leader kind of like equivalent up to some additive term, which is bounding how much you can lose in one round. And then the next step is showing that, well, so now I have this state perturbed follow the perturbed leader that doesn't know the last one. And then I have a state perturbed be the leader that knows the last one. So when you think about it, so okay, one of them is looking at the average until time t minus 1 adds a little bit of noise. The other one is looking at the average until time t adds a little bit of noise. And then based on that, they decide, based on that, they tell the agent what to do. Like for example, with the rainy or rainy bike car example, if that quantity in the noisy version is greater than half, the agent is gonna decide to drive, otherwise it's gonna decide to bike, right? How likely it is that these two randomized quantities will lead to different actions? It turns out that actually in most of the rounds, there's a coupling between the two randomized algorithms, that the two randomized algorithms will exactly lead to the same optimal action from the side of the agent. And then combining that with the fact that a state perturbed be the leader is not that far from a state be the leader, you can get the final result. So the next two steps are to formalizing what I just said in both. Let me try to do that. Now consider a second hypothetical algorithm. Consider another hypothetical algorithm. So I'm going to call it a state-perturbed leader. So what does it do? So it's going to go with a forecast PT tilde, which is basically the same as the leader, but I'm going to add a noise. There's going to be 1 over t summation t prime from 1 to t. So I have the xt prime, and now I'm going to add a noise. Let's call it nt tilde of t. And this nt tilde would be a uniformly drawn from distribution 0 to 1 over epsilon. So the same distribution as my other noise nt. And these are going to be IAD across time. I should have mentioned that. In fact, it is not necessary in the analysis, but for the sake of simplicity, just imagine that every time that you make a decision, you draw this noise again independently from the same distribution uniformity drawn variables. Right? Now, here's a claim.
Can I ask a question?
Yes.
Can't we just take the noise one time at the beginning and then go with that
No.
single noise?
Because you're dividing by t. If you add one more time, you're going to divide by t plus.
Oh, I see.
Great point. You can do that. Just going to be messy there. So I will do something similar. I'm going to add the noise to the first one. All right, so this is the lemma. If I look at the expectation of summation t prime from 1 to t, utility of the agent, when does best response with respect to State-Perturbed be the leader. Then I claim this is the greater than the expectation t prime from 1 to t utility when the agent is being best response to be the leader, the state be the leader. Oof. Right, so I guess the only real proof for this, the simplest proof maybe, is that P the leader is basically an algorithm on the sequence x1, x2 to xt. This is true for any t, but yeah, not good. So this is how you run be the leader. Now I can look at a slightly different sequence where, remember, so even though these guys are 0, 1, I can always think of even perturbing the state, making it a number between 0 and 1, because at the end of the day, you have these linear utility functions, and really don't think about predicting 0, 1, think about predicting just some number that is positive, and you want to predict that number. So you can always perturb the state, set up exactly the same problem, relaxing the assumption that these numbers are either 0 or 1. And the same analysis for be the leader is going to work. All right, so now this is the trick. So I'm going to look at a slightly perturbed instance when you have x1 plus my noise, n tilde, that's time one, and then time two, and the rest, they're going to be exactly the same. And then I'm going to run the BDL leader on this sequence. And I claim this whole thing is equivalent to basically running the State-Leader, so it's equivalent to running the State-Perturbed-Leader. Right? Do we agree on that? So these two algorithms are the same. And then we oh, and actually let me change my lemma a little bit to make my life easier. So I'm gonna show the following. I'm sorry, I have to change the leader. This is true for every action and XT. Somehow I want to compare myself with the fixed action. The other lemma was also correct, but it needs a one extra line, so let me actually go with this version. All right, so yes. And let's see why this is correct, because if I run the State-Perturbed-Leader leader on this sequence, then I'm going to be better than any fixed action on this sequence. So therefore, expectation of T prime from 1 to, let's say, any T, U of best response, PT tilde, and XT, because of the previous lemma, would be greater equal than essentially the expectation you get from any fixed action. So expectation, this expectation over this noise I added, expectation of summation T prime from 1 to T, U of action A, now it's a fixed action, and X T. Let me be a little bit careful here. So let's call these guys XT tilde. So this is going to be X1 tilde. This is going to be X2 tilde. This is going to be XT tilde. I'm going to use actually tilde here. So if I run my State-Perturbed-Leader and this sequence is going to be better than any sequence, any fixed action on the same. That's what I was. Yes. I think something very simple. So you have these X1 to XT. I'm adding a noise N tilde to the first one. I'm running beat the leader on that sequence. So the left-hand side is the agent utility when does best response against this sequence. Right-hand side is a fixed action against this sequence. And the reason that left-hand side is greater than right-hand side is because of the guarantee of beating. All right. Now, we're almost there. So this is going to be expectation. So remember, the utility is going to be linear as a function of this second input argument. So because of that, I can separate out the noise and everything else. So I can write this down as the expectation of summation T prime from 1 to T, U of best response with respect to PP tilde, and make this one to be XT. In all rounds except for one, I'm fine. In round one, there will be an extra term, which is expectation of utility best response with respect to T1 tilde, and then you have a noise. That's the left-hand side. And then on the right-hand side, something similar. So this is going to be greater or equal than expectation. There is no expectation anymore. Summation T prime from 1 to T, U of A and XT. And then I'm going to bring out the first term. So you will have expectation of U of A and the noise again. I should mention I made an assumption added to the set of assumptions that I started the lecture that utilities are numbers between 0 and 1. So when I define the utility, let me add this assumption here, assumption. The utilities are mapping actions and say the state to a number between 0 and 1. So they're bounded by 1. So I need a bounded utility. And now when you think about this quantity, this is going to be order 1 over epsilon, right? Because this is kind of like the order of your expectation of NT. The linear function is Lipschitz. If the utilities are bounded, this is going to be order 1 over epsilon. This term is also going to be, because of the same reason, order 1 over epsilon, up to some constants. And therefore, the proof of the law. Yes.
So I understand the claim and lemma. So the only question I have, the construction of this hypothetical forecasters are based on, you average from time 0 until the current time that you allow the current state.
Right. Yes.
So what happens if you just use the current xt at the moment? Can we also do that?
You mean not adding the noise? Or
No.
so here, all I do is I'm running the B-Leader, which includes the current XT, and I add a little bit of noise to it, which is equivalent to perturbing maybe the X1 with the noise and then running the B-Leader.
I think my question is that instead of that summation t from t prime from 1 to t, can't we just use the p tilde based on xt at the current time t? Because
so rather than looking at the historical average, just looking at the last one, that's not going to have enough information because it's adversarial sequence. You see, like I can easily mess up with such an algorithm by giving you a wrong sequence. So you need to really look at the empirical average somehow. But the deterministic looking at the empirical average is not enough. All right. So far, we have a series of claims, and I think this is the more interesting one. So I'm going to show somehow the two algorithms, Follow-The-Perturbed-Leader and Be-The-Perturbed-Leader, are pretty much the same algorithm. And let's actually think about that. Use a geometric picture for, so imagine this is it's a real line. I'm going to tag 2 points. So one is the empirical average excluding time t. So it's going to be this point, which is 1 over t minus 1 summation t prime from 1 to t minus 1 x t prime. And then the other one is the empirical average of time t, which can be lower or higher. For now, let's say it's just like higher, doesn't make a difference. They're just like 2 points on the real line. And this perturbed empirical frequency is just adding noise to this quantity. So the first one from the Follow-The-Perturbed-Leader is basically adding the noise. This is the interval of length 1 over epsilon. I'm just like looking at the PDF. But this length is 1 over epsilon. And same thing for this guy, right? So you will still have kind of a uniform distribution. This is the lower support, goes all the way to here. And this length is also 1 over epsilon. Now here's the point. So this quantity, this length here, is going to be no more than 1. Because this is the average of t things versus average of t minus 1 things, and out there are numbers between 0 and 1, so it's at most 1. And this length is exactly equal to that length because these are 1 over epsilon, so this is going to be at most 1 as well. So as you can see, the two PDF, they have a huge overlap. This part is the overlap. And now here's a kind of like a nice fact. If I look at the distribution of the first noisy empirical frequency, condition on landing in this interval, there is going to be uniform distribution in this interval. We can say exactly the same thing about the other one. So if I look at the distribution of the noisy empirical mean, but I'm conditioning on the event that is in this interval for the other quantity, still it's got a uniform distribution. And this is exactly the fact we're going to exploit to kind of say that, hey, there are some bad events when you have noises in these regions and the probability of that is small. But when they are in this common region, you essentially are drawing from the same distribution, which is uniform in this common region. So let's formalize this. The lemma. Basically, I want to say that the expectation that you can get from time t prime to 1 to, let's say, t by following pt hat, which was this is the Follow-The-Perturbed-Leader, and the xt. This minus the expectation of t prime from 1 to t. This is what you can get from ptt, which was perturbed version of the B-leader. So this difference, when you can think of the absolute value sense. It's going to be at most order epsilon. Let's prove this fact. All right, so on this side, so that we have the picture. So think of the first quantity, so the expectation of summation t prime from 1 to t, utility of pt hat and xt. Okay. Now, this is going to be equal to summation t prime from 1 to t. Of course, the expectation, the linear operator, expectation u of p hat and xt. Now, take up just one of these quantities, so the expectation of utility of the sites is below. So there's best response to this, best response to that. Sorry for my. The utility of best responding to pt hat and xt, right? You can write it down as this expected utility when you're conditioning on the event that your random pt hat is a random variable, right? Because it's just the noisy version of the empirical. Condition on the event that pt hat is in this set OT. So what is OT? So OT is the constant here. Times the probability that pt hat is indeed in OT, plus the expectation, blah, 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 some conditional expectation, times the probability that pt hat is actually not in OT. So this is bounded by one because this is just going to be some utility in one round. Utilities are bounded between 0 and 1, so this is bounded by 1. What's the probability of this event? Now, these are distributions where the height of the PDF is epsilon. So the probability of this event that something is not in OT, let's say PT hat, would be basically the area of this rectangle, and that's at most epsilon. Right? Now, this is the interesting part. Probability that PT hat is in OT is actually equal to the probability that PT tilde is in OT. Right? Because just the area of this rectangle. And then if you're conditioning on the event that PT hat is in OT, then PT hat will have uniform distribution. This is equivalent to replacing PT hat with PT tilde. So I claim that this is also equal to the expectation of U best response, PT tilde, XT, conditioning on PT tilde is in OT. And this is basically very, very basic coupling in the sense that condition this event, the distribution of this guy is just uniform distribution. You can say the same thing for both P hat and PT tilde, so I can replace PT tilde with PT hat, and vice versa. Okay, so what is this quantity? This is going to be the expectation of the utility of best response PT tilde XT, indicator of the event that PT tilde is in OT, plus some order epsilon additive term. And this is at most the expectation itself. And not only in aggregation, these two algorithms are pretty similar. In fact, point by point, they're pretty similar in terms of expectation. So what they show was that, hey, the expectation of PT, okay, so this implies that expectation of utility of best response to PT hat and XT is at least the expectation of the utility of best is at most actually. Right, that's fine. Best response to PT tilde XT plus order epsilon. But really, like the argument is symmetric, right? Because like with the start from PT tilde, write down exactly the same thing and follow the same chain of inequality. So similarly, we can also say the expectation of U of best response PT tilde and XT is the same expectation of best response. PT has XT. That's order epsilon. So term by term, they are within additive difference of order epsilon from each other. But if you sum them up, you get the law. This is kind of nice, right? Like you kind of a very nice coupling argument between Perturbed-Leader and Follow-The-Perturbed-Leader. And now let's put every pieces together. Somehow my Follow-The-Perturbed-Leader algorithm is not that far from Be-The-Perturbed-Leader. Why? Because their difference is order epsilon times capital T. At the same time, Be-The-Perturbed-Leader is not that far from Be-The-Leader because their difference is order 1 over epsilon. Therefore, the difference between Follow-The-Perturbed-Leader, so now let me actually write down the final corollary of all. Yes, Mohammed.
And before you delete the right half of that, I just want to say a quick thing. So when in that last part, when you say you you say it's linear between x1 plus n, so you take out the n part. It's an affine function, so that's not gonna be actually the utility function because it was x times something plus 1
You
minus
get an
n
extra
something.
constant.
Yeah, that's a kind, yeah, there is something.
Yes, that's really what they meant.
Yeah. If you added day 0, then this would be exactly as.
Right, so alternatively, what you could do when you're comparing the two, you could get rid of those constants at the first place.
Yeah.
Subtract that first, and now you have
Yeah,
linear
exactly.
functions. And then
That's
I'm like 97% precise with these ones. The 3% are just like some hand-wave arguments I do in my head, and I expect that you guys do the same thing when you read your notes. All right, so let me put everything together. Currently, agent external regret when follows the State-Perturbed, Follow-The-Perturbed-Leader at time t is going to be at most epsilon times t plus order 1 over epsilon. This is the gap between State-Perturbed be the leader and the state be the leader. And this is really the gap between agent regrets under two forecasts. One is
the first one was followed.
State-Perturbed. Like the State-Perturbed be the leader and a State-Perturbed follow the perturbed leader. State-Perturbed follow the perturbed leader. And this is the gap between a State-Perturbed be the leader and a state's be the leader. Thank you. Now set epsilon to be equal to 1 over a square root of t, therefore. Cool. So let's actually have a break, maybe for say 10 minutes. We will look back and I'm gonna tell you how you can induce the no internal regret learning behavior and how it is related to this concept called calibrated forecasting. But the punchline here is that by just like perturbing the average empirical frequency, you can actually induce external no regret learning. And now if you map this tool to the learning in games, so you have agents, and then for each agent, I'm gonna say some forecast about the action profile of other agents, and I do the same forecast for all the agents at the same time, then they are gonna have no external regrets, and therefore they converge their course correlated. But as we discussed last time, this is a very weak notion, so we would like to have convergence to actual correlated equilibrium, and this is only achievable by inducing no internal regret, and that's what we are going to show after the break. Right? All right, let's continue. So now the goal is designing a kind of a refined forecaster that induces no internal regrets. And it turns out that that kind of forecaster is deeply connected to this kind of like notion, which is, I would say, a way of describing an unbiased prediction. But it's not really unbiased prediction. Unbiased prediction has a mathematical definition which is different from calibration, the notion we'll talk about soon. But it's fairly connected. And I guess it comes from the following frequented way of looking at the forecasting problem. Suppose I tell you, well, it's going to rain with probably 30% today. How you can assess that is a good forecast, right? So that's kind of like very basic question. If somehow you have a way that you can sample from the rain effect, then one way of doing that is, hey, I'm going to take some samples from that rain event, and I see whether the probability of rain matches the 30% that you told me. This is pretty much like a Bayesian approach that you have access to a prior, you have access to a sampling device, and therefore you can check whether the forecasting is doing a good job or not. But then, now imagine you don't have access to that sampling device. Of course, otherwise the problem would have been trivial. And instead, you are interacting with that forecaster multiple times. In some days, it's going to tell you that, hey, today is going to rain with probably 30%. In some other days, it's going to be 40%. You can just naively assume that, well, maybe rain was an IID event throughout the year, and therefore these are just like samples of that IID event. But this is just wrong because rain is not IID across time. And now you can start thinking that, can I kind of like compare the forecaster itself? I look at all the rounds that the forecaster said rain is gonna happen probably 30%. And then looking at just those specific rounds, I see what is really like the empirical frequency of rain. Is it 30% or not? It's kind of comparing the forecaster with itself to figure out whether the forecaster is doing a good job or not. And that's the notion of calibration. So calibration is really comparing the forecaster with its forecast internally, endogenizing the task of figuring out whether the forecast is accurate. And with this introduction, let me actually formally define the notion of calibrated forecast. I'm still going to use the same setup as before. So we have these unknown states, xt, that are going to be either 0 or 1. And we still imagine that you have a sequential forecasting game. There is an online forecaster. Decides on a forecast, gets to see the unknown state, and you have capital T number of the same game. Now, imagine that the forecaster is generating a sequence of probabilities. Forecaster generates a sequence. Let's call them P1, P2, all the way to P capital T. So this is for the probability that x is equal to 1. And then suppose the unknown state is the following sequence. Unknown state is the sequence x1 to xt. Then we have the following definition. So definition, we say sequence P1 to P capital T generated by the forecaster is epsilon, and I'm going to put it in the parentheses, FV calibrated. And F and V, so this is Dean Foster, this is Ricky Bora, and I'm referring to the Foster-Bora 1998 paper, which introduces notion of calibration. The paper is on Canvas that you can actually download it, and it is pretty nice. So the sequence is epsilon FV calibrated for the sequence of states x1 to xt, if and only if the following is true. Let me first define a few things. So I'm going to define, let's say, for a probability P between 0 and 1, I'm going to define tau T of P to be basically all the rounds T from 1 to T, such that my forecast was equal to P. There's going to be a subset of rounds, and imagine that you have capital T number of rounds based on different probabilities that the forecaster is predicting. They're going to be partitioned into different sets. And then the cardinality of tau TP, we should think of it as the number of times that you had predicted P, let's call that NT of P. And then finally, I'm going to define rho T of P as the empirical frequency of having a 1 in those rounds that you predicted P. Let me write it down. So this is going to be equal to the summation of xt for every single t in tau of T of P divided by NTP. Is it clear? So I'm looking at all the rounds in which I predicted P. I see how many ones I have. I divide by the number of those rounds. That's the empirical frequency of having a 1 in the round that we predicted P. So we say we have epsilon calibration if the following is true. If I sum over all P's, and this is kind of a, you should think of it as a summation over all numbers between 0 and 1. But the summation is well defined because I only care about those that are either P1 or P2 or PT. So sum over all P0 and 1, and then I'm going to look at NTP divided by T. Let's say the difference between rho TP and T. That round, so for a given P, I'm just like penalizing myself by the factor rho TP minus P, which is the difference between the empirical frequency and the actual P. And I'm essentially adding that up over all rounds after renormalization. This is what this notion is about. So we say it's going to be epsilon calibrated if this is less than or equal to epsilon. So this is the potential calibration. Right. And then one easy consequence. So here's the claim. The forecaster is epsilon calibrated with respect to the unknown sequence F1 then the agent that picks action AT has, which is in best response with respect to the forecast sequence PT, think of it as argmax of similar settlement before UA and PT for every action A in my curly A. Right. And if I think of this sequence, I claim the following is true. Then it means we have. Essentially, I want to say that the agent is going to generate a spread of action that has a small internal regret. And the internal regret is no more than epsilon. But in other words, for every pair of actions A and A prime, I can say the summation T from 1 to capital T, if I look at all the rounds in which my action AT hat was equal to A. Remember the definition of internal regret? So just a recap from 2 weeks ago. Internal regret, when you think of it, is actually pretty similar to calibrated forecasting. You're comparing the sequential decision maker with itself. So I'm looking at all the rounds that I'm selecting action A, and I say in all of those rounds how much benefit I would have received if I had played another action A. Right, so that's kind of like the definition. So right, so this we look at all the rounds I'm playing action A, and I look at the extra utility I could get by deviating to action A prime in such a round. And this quantity should be smaller than epsilon, so that epsilon times 2. So that means that the agent has a small internal regret. Internal regret. For swap regret is at most absolute. In fact, swap regret is at most absolute. Internal regret is at most n times epsilon. Or order of epsilon. Okay. Let's see why this is true. It's pretty much at the level of the definition. I think the definition carries a lot of interesting insights. I'm going to look at all the rounds that I'm playing. I'm looking at the definition. And now when you think about this round, we decided to play action A, so that means that we received a forecast that the best response we expect to that forecast was action A. Right, so therefore we can say this is equal to the summation T from 1 to T, let's say. And then summation over all possible P's. Indicator that PT was equal to P and then I'm looking at action A prime xt minus the best response with respect to Pxt. Let's see if we all agree with this. Do we agree with this statement? I'm just
Will it be the case that in some other, for some other P's also, the same action A is AT hat is the best action? So we should include them.
they are included. So somehow for any P, let's say you just pick one of the actions as the best response, that might be the case that for different P's, the same action is selected. I'm just saying, rather than taking a summation over actions, rather than going over around and see whether action A is selected or not, I just go over probabilities where forecast was P and somehow best response with the tie breaking. You need to do some tie breaking. For example, there are multiple best responses. You fix the tie breaking rule. So with that fixed tie breaking rule, then my action has been best response to P. That's what I'm trying to say. Let me write it in. Just like something very simple. So I'm sure a P is such that actually maybe I should have said that A is in the best response of P. Summing of all probabilities where A is the best response to P. And then I look at the indicator, and in that round the forecast was P, and then I look at the difference. Right. This is right.
So you don't need the indicator, right?
I do need the indicator because I'm not gonna look at the rounds in which PT was not equal to P. I don't know how to encode that. I'm just gonna look at the, so you're not looking at all the rounds, you're looking at the subset of the round where prediction was actually go to P. And in those rounds, you wanna compare your deviating utility with the utility that you're getting. So actually, you need to indicate there. And this is equal to the summation P in 0, 1 over all P's that A is in best response of P. Now I'm going to use the fact that my utility functions are going to be linear in the second environment. So therefore, if I look at the U of A prime and X2 and I sum over all T, so let me do that. So it's going to be sum over T from 1 to capital T. U of A prime change the order of summation. So this is now going to be exactly. So it's going to be U of A prime summation one not instead. Let me write it down. So PT is equal to P times XT. This is a little bit weird though. Okay, that is fine. No, I think it's okay. Yes. Right. Basically, right, I think this is correct. Minus U of first response of T. I'm using the fact that U at the second input argument is linear. And again, I have the summation T from 1 to T, indicator that PT is equal to P times XT. And these are relevant summations that we discussed. So this is like the summation of the ones that you get in rounds that you're predicting P. So let me multiply the whole thing by NTP and divide by NTP, which is the number of rounds in which you play P for that particular P. So now this is going to appear here. There as well. We are almost there. Let me also divide this side by 1 over T. So that I have this as well. This is the empirical measure that we are discussing for the rounds that you are predicting P. And then the point is that this is not that far from P. In the rounds that you actually care about, the rounds that you suggest P, this number is not that far from P. That's the in aggregation, that's kind of the currency of calibration. So let me now do the following. So I'm gonna add and subtract two terms. To both of them, right? So I'm going to add a u of a prime and p and subtract u of a prime and p. What I'm going to add and subtract. And I'm going to add u of best response of p and p and subtract the same thing. And I think we are going to be almost there. Mhm. First, there is a term which is about rho TP minus P. Let me bring that out first. So I'm going to have this thing, which is going to be, so this is going to be equal to two terms which are going to be eventually as well. So P in 0, 1, such that A is in best response to P. And I will have NTP divided by T, U of A prime, and now rho TP minus P. That's the first noisy term. And then I have the summation over all P, again, 0, 1, where A is the best response to P. And now I'm looking at this term minus this term, so this is going to be NTP divided by T times my utility, my best response to P, and then the state is rho TP minus E. I'm using the fact that I have affine function. All right. And then the remaining term is basically just right. So let me write down the remaining term, which is summation over P in 0, 1. Again, A is the best response to P. And I have NTP divided by T. And what is this term? So this is going to be U of A prime and P minus the U of best response to P. I claim that this is less or equal than 0 because you are best responding to P. So if you're looking at those rounds in which you're listening to forecast P, then A prime wouldn't be a good thing for you if the actual forecast is P not XP. So this is negative. But now these two terms are small. Why? Because utility is bounded. So the utility that you can get from best response P when the forecast is the difference, it is going to be bounded by the absolute value of rho T P minus P when you think about that, right? Because it's just like some number times this probability plus 1 minus this number times another quantity, so some quantity times this number plus 1 minus this probability times this quantity. When you change, let me write it down in case you don't see what I'm saying. So I guess when you look at one of these terms, right? So it is going to be, let's call this an action A hat. This is nothing but just U A hat of 1 times, let's call this alpha, times alpha plus U A hat of 0 and 1 minus alpha. And I guess what I'm trying to say is that if alpha is 0, this is going to be pretty much equal to just the U hat of A and 0. And then you can say the same thing here, and they're going to cancel each other. Right. Yes, if the utility was not affine, it was linear, then this was bounded like this. If it is affine, you get an extra term that extra term actually cancels with things that you have here and you have there. If you do the calculations, so then the bottom line is that this is going to be negative. This is going to be at most rho TP minus E. It's going to be at most rho TP minus E. I'm waving a little bit my hand so that we add a O here because there are going to be hidden constants. But then the bottom line is if you multiply that by NPP over T and then do sum over P's and do the same thing, this is the calibration. And these are. So therefore, the whole thing, the new fixed by theorem, so it's going to be order epsilon T. So the whole thing is going to be bounded by order epsilon. And I already divided by capital T. So if you rearrange the terms, you get the results. So I waved my hand a little bit in this last step of the computation, but really what's happening is that these utility functions are usually, you can think of them without associated to be linear, not even affine, because the constant terms are gonna cancel when you look at this minus that at the first place. You could cancel the constant term even there and say without associated, I'm just like looking at linear terms, right? Or alternatively, you could just say these constant terms are not gonna contribute to anything more than order 1 over T regret, whichever you prefer. So at the end of the day, this is gonna be epsilon plus some constant coming from U of A hat 0 affine term that you didn't cancel. And I encoded everything in this O notation. Sorry if this is not clear enough. I hope I could convince you that you could think of these U's as just a linear function of the affine function and not its convergence. All right. So that means that calibration is kind of like the goal that we should shoot for, because if we can get calibration, then we will have agents that will have no internal regret, and that was the goal that we had in the last lecture. Is there any question from this part? Yes, Mohammed.
We are kind of, calibration is kind of much stronger, right? So it essentially says sum over all actions is at most epsilon, but here we only need whenever the best response is A. Right?
No, so calibration is also, I mean, kind of like you're saying,
it's sum over all P's, but here we are just using those P's that are A is best response for them. So I was thinking maybe even if you just forget about swap.
I'm not using P's that are best responsibility. Actions are best responsibility.
Actions that are best responsibility.
Right, and here, so I guess the way to think of that here, the terms that you have each one is corresponding to
so some action, let's say.
So around that you get some forecast P.
Yeah, and then my point is that so maybe not only swap regret is at most epsilon T, but the entire internal regret is at most epsilon T, because your calibration error is sum over all actions.
No, so actually internal regrets. Data are proof that shows internal regret is going to be at most epsilon T when you have the epsilon calibration, not faster work calibration. I don't think in faster work calibration you can get a small internal regret. You can only get a small swap regret, which I just called the internal regret, but I don't understand what you're saying. Let's actually take it offline. Right? And yeah, so I don't think what you're saying is correct. I can show it maybe after. All right. So now this is kind of like the final step. So the final step is coming up with an algorithm that can give you a small calibration. And there are many ways of doing that. In fact, by now we know this problem is fairly connected to online convex optimization. We have a very good understanding of the best algorithm for calibration problem. I'm not gonna actually go over the best algorithm. I'm just gonna use the algorithm that we had for Blackwell approachability, in particular, the result that we had for Blackwell approachability last time, and show you how you can cast the calibration problem as an instance of Blackwell approachability. So we're gonna go over the steps carefully. And as a result of that, you will get an algorithm as long as you can solve the Blackwell approachability problem. And if you recall, last time I talked about regret matching, which I showed you the algorithm. I never showed you why it works. The same algorithm, you can use it after you do a reduction to get calibration. So let me do a recap of Blackwell approachability for those of you that probably don't remember all the details. So recap. So Blackwell approachability is a game between two players. It's a sequential game. So you have player one, say, picking a strategy X from curly X. And then you have player two, playing a strategy Y from curly Y. And typically we think about what I call vector payoffs. Let's say a function U that maps curly X Cartesian product with curly Y to some d-dimensional vector R in Rd. And then the game is endowed with the target set. So you have a target set F, which is convex and closed. It doesn't need to be compact. It should just be closed. And these sets are typically assumed to be compact sets. Sometimes you need them to be convex, but not necessarily. So either compact sets in their own space. And that space is different from RD. And then the approachability problem is basically this problem that player X would like the payoff vector to land in target set S. And player Y, player two, would like the vector payoff to not land in target set S. And then they play this game sequentially. It's a sequential game. We call it Blackwell game. At each round T, for time T from 1 to capital T, player 1 goes with some strategy XT, player 2 goes with some strategy YT. So this is in curly X and this is in curly Y. And then they see each other's strategies, or let's say they see either the pair XT by T, or equivalently, you can say they see the vector payoff in that factor, U of XT and YT. It turns out that this is equivalent. And then the game continues. So the goal of player one, which is the goal that we have, is what they call approachability. So you would like to have generate a sequence of actions or sequence of plays for player one, generate a sequence x point to x capital T, such that somehow if I look at the, let's say, L infinity norm of U, let me do it. So the distance U bar and target set S should converge to 0 as T goes to infinity. And U bar is 1 over T, summation T from 1 to capital T, U of X T and Y T. So this is Blackwell approachability problem. And we usually sit in the position of player one who would like to generate that sequence. And then we had this theorem from last time, theorem we say target set S is approachable if and only if the target set S is half a space forcible. So if you don't recall this notion, so what does that mean? That means that consider, let's say, a half a space H containing this. So the picture is that I have a set F, and I consider a half space that contains a set. Somehow approaching this half space should be easy. And for stability means that consider such a half space, there should exist a good strategy for player one. I'm going to call it X1H, such that U of X1, H, and Y is always in the half space for every strategy that the second player plays. So somehow for any half space, so we say it is half space, first of all, it is true for any half space. And therefore, the Blackwell approachability theorem is saying that a set S is approachable if for any half space containing S, you have a good strategy, meaning that for any half space containing S, there exists a strategy that depends on that half space. It can change based on the half space that you pick, so that the utility vector, the vector payoff, is always in H regardless of what the other player is, if you play that strategy. And now the approachability theorem reduces to just checking whether the target set is half a space forcible. So you need to search over all the half spaces containing S and see whether you can find actually good strategy for those half spaces. All right, so this is the recap. So now what I'm going to do is to cast the calibration problem as an instance of Blackwell approachability. And then we are going to show that instance is approachable by using this theorem, by checking whether every single half space containing S is forcible. That's the mechanical way that we learn last time to solve online learning. And this is an example of online learning. And this is now related to your concern about discretization of the probability aspect, because now that we are designing an algorithm, we need to be careful how to discretize the space. And it shows itself in the game that I'm just gonna introduce. Is the plan clear? Like, why are we using Blackwell approachability? So we are trying to reduce calibrated forecasting to Blackwell approachability. And then we have this powerful theorem that, if you can show the instance of Blackwell approachability that you reduce to is approachable by checking half space forcibility of every single half space, then there is an online algorithm that solves the calibrated forecasting. And that's the online algorithm that solves Blackwell approachability. The regret matching algorithm that I talked about last time. And I promised that I'm going to post the analysis of why that works on the canvas. I never did that. I just realized I will do that maybe after this one. Reducing calibrated forecasting to Blackwell approachability. Right. So let me write down the notional forecast. So we say P1 to PT is epsilon calibrated for sequences state x1 to xt, if summation over p, ntp divided by t times the rho tp minus p is smaller than epsilon. Okay, so that's the problem you want to solve. Which means that I'm gonna generate a sequence p1 to pt that for any sequence x1 to xt is gonna be calibrated. I'm gonna solve that on a learning problem that you get to see x1 to xt, and you generate a sequence p1 to pt such that you have this quantity. Now, this is the game. Let me define a Blackwell game in the following fashion. So Blackwell game. This is the picture I would like you to have in mind, kind of related to discretization. So imagine this is the probability space. So you're just forecasting numbers between 0 and 1. So this is p equal to 0. This is p equal to 1. And now I'm going to get enough distance somehow from 0 and 1 for a technical reason that will be clear soon. And I discretize the space linearly. So I'm going to pick these points. Let's say I'm going to pick m points that are in the following way. So they're 2i minus 1 divided by 2m, for I from 1 to m. So this is 1 over 2m. This is 3 over 2m. And then the last one is 2m minus 1 over 2m. So if you notice, I'm keeping some distance here and here. I'm not having any probabilities there. So this distance is 1 over 2m. And this one is also 1 over 2m. And now think of an algorithm that eventually is only going to use these probabilities. I'm not going to use any other point in my forecast. I'm just going to go with these numbers. And this is really like a discretization. Right, so what is x? As I said, I'm only going to use these numbers. So x is just going to be 2, let's say 2i minus 1 over 2m, I from 1 to m. And really, I think you need to call this maybe another, let me be a little bit more careful. Let me call let x to be the simplex over another set x hat. And x hat is the set of all these probabilities. It's going to be the set of everything that is 2i minus 1 over 2m, or I from 1 to m. Because I want my algorithm to actually pick the distribution of our probabilities. Therefore, this is going to be my strategy space for the first layer. And then the second layer is simple. So again, y is going to be, let's say, delta over simplex over some other y hat. And y hat, think of it as mixed strategy and this pure strategy. This is also mixed strategy. But the pure strategy space is going to be only 0 and 1. Okay? And you really should think of this adversary as the one who is deciding on the states. I go with the probability, adversary decides on the states, and somehow on average, adversary wants to screw me up. And now it should remind you very much like the calibration problem, right? So let me define the vector payoff. So I'm gonna define my vector payoff to be for any, if you recall last time, so we were defining vector payoffs were defined in 2 ways. So one was for a pair of pure strategies, and then we talked about if the players are playing mixed strategies, you get extension. So let me go with the hat version. So u hat of I, the strategy picked here. Actually, let me use a slightly simpler Yeah, keep in mind that these are the points. So I'm gonna let X have to be just a set of numbers, 1, 2, n. Right, and then when this player picks I, that basically means that the forecaster has picked the point 2i minus 1 over 2m as the u hat of I and some strategy X here. I say it's going to be equal to X minus 2i minus 1 divided by 2m. The forecast minus the probability times the vector here. So you have an m-dimensional vector. Every time that the forecaster goes with probability 2i minus 1 over 2m, and the adversary goes with x, I'm going to put the difference on the I coordinate of the way. Let me give you some time to look at this down. And we have this other extension, and if I give you, let's say, some distribution over probability, let's call that maybe R. So this is a distribution over numbers of 1 to m, right? And I give you either distribution over 0 and 1, which is P, then this is going to be nothing but just R minus like P minus expectation of Pi hat when I is drawn from R. And then write it in, it's going to be basically sum over I from 1 to n. This is going to be Ri, the probability that you play I, multiplied by P minus 2i minus 1 over 2m times Pi. So this is kind of like how you should think of the mixed strategies. Now suppose the two players are playing this sequential game. Somehow as a forecaster, I'm going to go with, so forecaster, think of it as really like player 1. Is going with the sequence of strategies I1, I2, all the way to IT. And then environment is a player 2 in Blackwell approachability problem. Is going to go with the sequence x1 to xt. Okay. Now, if I look at the average vector, right? So u bar would be equal to 1 over t summation t from 1 to capital T, and then I go with u of I t and let's say xt. Let's write it down. So this is now going to be summation 1 over t, t from 1 to capital T. And then in the I coordinate, I'm gonna, by t coordinate, I'm gonna add xt minus 2 it minus 1 divided by 2m. And then I add up those vectors, right? So now let's look at this L1 norm of this vector. What does the L1 norm of this vector look like? So every coordinate corresponds to one of these possible probabilities. So it is basically the summation over, you can say maybe all the p's in the set 2i minus 1 over 2m, or I equal to 1 to m. Such a summation, right? And then you're subtracting two terms in each of the coordinates, and those are the ones that you're adding on. So that's just going to be the empirical frequency of xt, empirical frequency of having a one. So it is basically the summation of all the xt's in all those rounds when it was equal to, or let's say p. Right, so p was equal to 2it minus 1 divided by 2m. This minus the 2it minus 1 over 2, which is the p set, right? And there's a 1 vector here. So I can now multiply this by ntp and divide by ntp. And if you do that, then this is going to be equal to summation over all the p's that's were in your discrete set, 2I minus power 2m, I from 1 to m. And then you have ntp divided by t multiplied by, this is really like the empirical frequency. So the rho tp minus 1. And that's exactly calibration. Right? And if you recall, the last time when I was explaining this technique of using Blackwell approaches to solve online learning, the idea was like looking at really like the micro foundations of the problem and trying to design the payoff vector based on that. We saw two examples of that where we were designing no external regret learning algorithms and no internal learning using Blackwell. This is another example that you basically say, hey, every time that probability I is suggested, then I'm going to put something in a row corresponding to that probability. And but if that something is the difference between the error in that round and the probability itself, in the actual state in that round and the probability itself. And now, if on average you guarantee that this is going to 0 in L1 norm, for example, then you will have calibration. Okay, so therefore, if, for example, you show that u bar is smaller than epsilon t as a function of t, then therefore calibration error can get epsilon to calibration. All right, so now let's see whether this game is approachable. So if we show that this game is approachable, after proper normalization, basically it's actually a square root, 1 over square root t. This is what the regret matching algorithm could obtain in the Blackwell approachability problem. So somehow we actually get 1 over square root t internal regret behavior as a result of that, which is the best thing you can hope for. This is a binary action problem, and in fact, if you extend whatever I showed you in a careful way to the case that you have multiple states, then by using the same reduction, you can get the right dependency on even the number of the states. And this is something that you will do in one of your assignments. But yeah, so for now, if I can show that the game is approachable, target sets, I have to tell you what is the target set, which is kind of clear from here. So what is the target set? So my target set S, imagine it's going to be the L1 ball with center 0 and radius epsilon. So I'm going to consider, so this is just a number. So what I want is that this number to be smaller than epsilon. So that essentially means that I want the vector u bar here lands in this point. And think of this as really like the L1 bar with radius epsilon, with centers. We can get such a thing, then we are all. So the rest of the lecture is about showing that this Blackwell game with this X and Y and this utility and this target set is approachable by checking that it is half a space forces for every single half a space that contains my uniform. Right. Any questions? Yes.
This request would also depend on M, right?
Also depend on M. That is absolutely true. I'm trying to see what would eventually depend on M.
And depend on T, so.
Right. Correct. So last time we discussed, right? So that the number of you're right. So the regret bound of Blackwell approachability problem is going to be square root T times N.
Yes.
So therefore, you're going to end up with right. So you need to pick M carefully enough to get full calibration, which would be something like if you balance the term, I think that gives it to the 2 terms.
Probably. So it's also regret, probably not T.
Right. So it's root T when you think of M as a constant, but if you include the discretization error in the calibration, then it's going to be T. But with my definition of calibration, actually, that's not going to happen. Because in my description of the calibration, I don't care how many discretization points. And that's why the Foster-Bora calibration is not a very meaningful notion of calibration. But then if you look at a stronger notion that takes into account the discretization, then you're going to get it to the truth, and that's what you are implicitly requiring. Let's chat about that offline. This is a very subtle point. All right, okay, cool. So let me try to show why this game is approachable. Let me start by a picture. Let's say for now, n is equal to 2, so you have a 2-dimensional problem, something like this, right? So I'm looking at this setting. Right. Let me change it to L2 ball, because that's going to make my life a little bit easier. And you will see this really doesn't matter. It should just be a small ball of constant dimension. It can be, right, so it should be a small ball. You can use LP for any P that is not L infinity, and you should be okay. So 1 and 2 are kind of equivalent up to constant. That's really like what I want to get. Then look at this L2 ball with center 0. Right, and let's not even look at that ball. So I'm going to look at this ball, right? So B2, 0 and 1 over 2m, which is really like a subset of, if you might be wrong, but I kind of feel, yeah, so let m to be large enough so that 1 over 2m is much smaller than epsilon somehow. And then I can say this ball is going to be subset of my even ball, L1 ball around 0 with radius epsilon, something like that. So m large. Okay. Now, if I think about the half spaces that contain this set, and when I'm considering this set, so I want to show approachability to this set. So if you can show approachability to this set because your original target set includes this set, then you're done. So now I'm looking at hyperspaces that contain this guy, and you should think of like different normal vectors. So I claim that basically the minimal hyperspaces that contain this set, those that are tangents to my L2 ball, like this one, or I don't know, this one, or this one. So those hyperspaces, I need to look at the site that contains the set. So they can be written in the following form. So let's say A is the normal vector. So A is the normal vector in R to the M. I think you can write them down as A dot product. So A dot product X to be greater or equal than -1/2m times the L infinity of A. Let's see if we agree on this. Just for example, like think of this half space. So this is the A that you want to look at. So one coordinate is 0, and then the other coordinate is a positive number. So now you want to say that, hey, somehow you're to the right of this block. So right, so A dot X is greater than -1/2m type A infinity. Is it clear? This is like basic geometry that's this ball. Everything up to rotation is going to be the same. So I can just like, look at these half spaces and then rotate to find the other half spaces. So what are these half spaces? The dot product should be greater or equal than this, and this is -1/2m. If my vector is normalized such that the A infinity is equal to 1. If it's not normalized, then this is just going to be the norm infinity that I'm looking at one direction that has a maximal spread, and then the other one is 0. So this is defining a minimal half space, and therefore this inequality. So I claim basically all these half spaces they can be described in this form, and all you need to show is that for each of them, I can actually find a good strategy for player 1. So you give me some A, and I need to find a good strategy for player 1 that guarantees you always land in this form. Okay. Now let's consider, so fix A. And now let's consider a couple of cases. The case number 1, suppose there exists some J, like one of these possible probabilities where Aj is actually equal to 0. Then I claim in that case, I can just say, hey, I will go with the following vector. So xj is equal to 1. So I'm going to put all the mass on j. And xk is equal to 0 for any k not equal to j. And I claim in that case, this strategy is going to be a force-field strategy for my half space. What do we need to check? We need to look at the utility that you get by this strategy in expectation. So the expectation of u of, let's say, of j hat and some other choice for the adversary x. When j hat is drawn from this strategy, let me call it q. Is basically what? So it is basically x minus 2 j minus 1 over n times ej. And then the rest are just zero, right? So you don't have any other coordinates, so you just have this value at that coordinate. Now, this is going to be in the bound that I want. Why? Because the maximum amount that x can get is 1, and 1 minus 2j minus 1 over m. You remember, so I kept this times 1 over 2m. So if you call this expectation to be vector u, then I claim that absolute value of u is at most 1 over 2m, and therefore you're done. So what does portability mean? For a half space, for example, for a given A, I should be able to give you a strategy such that you are in that half space. And actually, you land not only in that half space, you land in the S, which is in the half space, so you're good to go. I can also do that calculation for you. So basically, A dot X would be what? So think of X as your U vector, right? So A dot X would be this bad notation. I use X here and there. So this X is different from that X. Then we use V for my vectors. Oh, actually, right? So maybe you did that. So A dot U. If I set U to be this vector, then what is A dot U? So A dot U is basically X minus 2j minus 1 over 2m. And this is greater or equal than minus 1 over 2m times right, so right, so if that is the case, I can imagine aj is equal to minus 1, right? So therefore, so aj is equal to 1. Therefore, this is minus 1 over 2m times 1. But this is greater or equal than 0. This is less than 0. And therefore, you are in the half space. It's a little bit geometric, but I think it's actually not very complicated. What I'm trying to do is that I pick a vector A, case number 1, if there is a coordinate that aj is 0, then I say, hey, here's my strategy. I'm going to put all of my mass on that coordinate. I just go with probability 2j minus 1 divided by 2m as a forecaster. Right? And now I'm going to show with this strategy, regardless of what x adversary picks, you always land in that half space containing S. The half space is this. If you satisfy this inequality, you're good to go. Now A dot U, remember A is nothing but, in fact, when I make this assumption, you can normalize and assume that aj is equal to 1 and all other aj's are 0. So therefore, A dot U is nothing but just x minus 2j minus 1 over 2m, which is positive because the maximum amount that this quantity can get gives you a gap of 1 over 2m, and this is negative, and therefore a contradiction. Yes, ma'am.
I think you said aj is 0, and then because the u has only j's coordinate, so when you get the dot product of a times u,
Oh, that's such a that you get 0. Yes, you're right. You're right. That's even easier than that. Thank you.
And then why are you taking expectation? Oh, it's under run.
I know it's a deterministic thing.
Deterministic.
It's a deterministic thing. But
Yeah.
I wanted to kind of look at the general case because I've seen one of the cases that you ran with. But thank you. Yeah, he's right. So if I draw j hat from that distribution, which is actually points math, and I'm going to get these, right, my aj is 0. So therefore, dot product of that a with this ej is going to be 0. So you have 0 greater or equal than something negative, therefore you're good. Now there are two cases. case 2 and case 3. So I think this case is when A1 is positive. I did the math right before the class, or I haven't made any mistake. So A1 is positive. I would say in this case, you're also good to go. All you need to do is setting x1 equal to 1 and then xk to be 0 for all k not equal to 1. Let's see why this is the case. Kind of doing the same calculation, your vector u now is going to be x minus the first probability, which is 1 over 2n times so x minus 1 over 2m times
1, yeah, because it's again determinant. So point mass on the first action.
correct, times E1. Now, if I look at the dot product, this is the case that is similar to what I was describing. So if I look at A dot product U, and imagine that I normalize such that A1 is equal to 1. So after normalization, this is just going to be x minus 1 over 2m. And this is greater or equal than minus 1. Why? Because the minimum value that x can get is 0. So if x is 1, you are good to go. If x is 0, this is still true. So therefore, in this case, you're also fine. There is a similar case you need to look at, which is when the last A, I believe, is negative. That is also an easy case. Let me do that for you.
That was for any AI, not just A1, for any I that would work, right?
No, not true. No, that's not true.
Because then your 3 cases wouldn't be partitioning.
I have a 4th case.
Oh,
Yeah. And the 4th case is the one that we need to randomize. The case number 3. Essentially, the case is saying that AM is a smaller than 0. In that case, I'm going to go with the following strategy. XM is going to be equal to 1. XK is going to be equal to 0. Or K not equal to M. And think of this as my strategy here. So if I look at U, which is again, I'm still using the expectation, even though you're really not taking the expectation. Of U of J hat and X, then this is going to be equal to now X minus 1 over 2M times EM. So AM is smaller than 0. Let's say normalize such that the absolute value of AM is equal to 1. That means AM becomes minus 1. So I'm going to normalize such that AM is equal to minus 1. Now, if you look at U dot A, it's going to be equal to minus 1 times X minus 1 over 2M. And now you want to show this is greater or equal than minus 1 over 2M times the L infinity of A, which is minus 1. Let's see if we can show this. So this is 1 over 2m. Now look at the left-hand side. Did I- If x is 0, it will find 1 appear at that. Come negative. See what is there. Is negative and we normalize that and use it to one.
Can I say something?
Yes.
If from there just forget about A1 is positive or negative or anything. And it doesn't matter it's A1 or AI or anything, okay? So let's say AI is something, so you're getting that product of x minus. Okay, suppose it's A1, suppose it's A1.
Let me finish my lecture. All right.
Okay.
So A
That's x squared minus 1.
it should be the analog of that case, but for some reason I don't see the math. Maybe I did a mistake here.
It should be x minus, the numerator should be 2n minus 1 instead of 1. X minus 2n minus 1 divided by 2n.
Oh, thank you. Excellent. Because you're right, because we are putting a math on this probability, and that's 2m minus 1. This I mean. Thank you so much. That makes a lot of sense. So let's do everything again. So if x is 0, you're good, I believe. So 2m minus 1 over 2m is larger than over 2m. If x is 1, and is negative. So, oh, but that's no, okay, good. But it's actually the actual norm infinity, because it is the absolute value of minus principle. Yes, so this is the inequality that you have to prove. You need to show that this is greater or equal than minus 1 over 2m again. So I'm normalizing such that L infinity is equal to AM is equal to minus 1. But then the L infinity is equal to 1. And the right hand side is minus 1 over 2m, times L infinity is equal to minus 1 over 2m. So therefore, this is all I need to show. That regardless of x being 0 or 1, this left hand side is greater or equal than the right hand side. So if x is 0, this is good, 2m minus 1 over 2m is positive, this is negative. If x is 1, that's now a tricky case. So this is going to be 1 minus 2m minus 1 over 2m. We had this distance 1 over 2m, so it's going to be minus 1 over 2m, and therefore we are still good to go. Thanks. And now case number 4. Yeah, so using Blackwell Approachability is very mechanical, but actually showing things can be subtle. So case 4 is if none of these cases happens, and if that is the case, so basically I'm going to have A1 to be positive, AM to be negative, and for every other J, AJ is non-zero, right? So that's kind of like the case. And think of it as I was starting with a negative number that is non-zero. I end with a positive number that is non-zero. I end with a negative number that is 0. And I cannot be 0 anywhere. That's kind of the sequence. But therefore, there exists some J hat such that you do the change of the sign. So AJ hat is positive, AJ hat plus 1 is strictly negative. Now, define two probabilities, so Q1 to be equal to Q1 to be equal to AJ hat divided by AJ hat. I'm sorry. The case 4 is when A1 is negative and AM is positive, because I don't have overlap, right? So AM should be positive, A1 should be negative, and then all are non-zero. So there is a J hat such that AJ hat is actually negative, and AJ hat plus 1 is positive. So when you do a transition from negative point to positive point, and then I get Q1 to be, say, minus AJ hat divided by minus AJ hat plus AJ hat plus 1, and Q2 to be AJ hat plus 1 divided by AJ hat plus 1 minus AJ hat. So this is kind of like a fraction between the two numbers. And I'm going to define the following randomizer strategy. So X, right, so this is the randomizer strategy. Now pick J hat with probability Q2, actually, and pick J hat plus 1 with probability Q1. Remember, so for showing for stability of this particular half space, I'm allowed to pick a randomizer strategy. It's something that I can do that. So I'm going to show that this randomizer strategy is the one that says, regardless of what X the adversary picks, you will land in the house. And the way define is figuring out these transition points, and then find these fractions, and that defines the randomizer strategy. In the interest of time, let me actually do another exercise, because you already saw how I proved it 1, 2, and 3. The exercise is not really like difficult. Exercise show U dot A is greater or than minus 1 over 2m, L infinity of A. If U is defined to be the expectation of U, J, your J, U of J and X, when J is drawn from, when J is equal to J1 hat with probability Q2, and is equal to J, sorry, J hat equal to Q2 and J hat plus 1 with probability. Then sampling J from this distribution, and for any X you get some U, show that regardless of the choice of X, this is equatable. And if you show that, then you have a Blackwell approach of it. So let me end at this point. I'm going to leave it at the time. But I hope I could convince you that Blackwell approachability, even though it might not be very easy to go through the calculation and show the approachability, but somehow it's a very mechanical way of solving online learning, very different ways of online learning. Either it's a sequential decision making, maybe it is calibrated forecasting, maybe it is obtaining internal regret, external regret, etc. And the power of Blackwell approachability is that this is if and only. So if there is a chance you can solve an online learning problem, then there should be a way that this is approachable. So if you set up the problem correctly, so that approachability is almost equivalent to solving your online learning problem, then checking approachability is an if and only condition for the existence of a learner. And you see like some magic happens here, right? So you see these inequalities, they go through very nicely. This is really because of the fact that the underlying problem is learnable, and you can see that in the form of this geometry and these inequalities. And that's it. So far, we covered external regrets, internal regrets. We have algorithm for those. We know calibrated forecasting. We know how a forecaster can induce agents having no external regrets, no internal regrets. The next time we're gonna switch topic a little bit, talk about what happens if, for example, we are in a combinatorial environment, you want to do learning, and then we are going to talk about forecasters in combinatorial environment. How should they change the way that they produce forecasts so that in acceptable running time we can do forecasting, and also we can do the decision. So with that, I'm going to end the lecture. Thank you so much.